Okay, so in the last lecture, it was discussed that what is the definition of the random variable. So usually the random variable is defined as a function on the probability space to the set of real numbers, right? So basically, we are given the experimental space omega. So omega is any set, and we are defining a function x from omega to r, x from omega to real numbers, and this function has certain property. So this is certain property of this function. So any such function we call a random variable. We call a random variable. So you have any doubt? It is better to unmute your mic and ask, right? So uh, yeah. So x is a random variable, and it is by random variable we mean that x is a function on the sample space, which is real valued function. Now this property is related to essentially the sigma field. So if you recall, what is the definition of sigma field? So if you recall, the sigma field is essentially the algebra of events. Algebra of events. What is the definition? Definition is it is a essentially subset of power set of omega. So on an empty collection f, an empty collection f of subsets of an empty set omega. So omega means essentially we are saying it is a sample space, and we are taking all some of the subsets of omega, not all the subsets. If we take power set of omega, then it contains all the subsets. But here we are saying that f is an empty collection of subsets of omega. That means we are taking some of the subsets. Omega is called, so when f is called a sigma field, or an algebra of events, So like you have Boolean algebra, right? So there are many examples of Boolean algebra. So similarly here, what are the examples of algebra of events? So for that, we need to essentially write down what is the definition. So this is the definition. This definition says that if you have any element of f, element of this family, then its complement must be in the family. Its complement must be in the family. What does this mean? This means that if A is an event, then its complement is also an event, right? So that is the first property. And second property is that if you have countably many events, a1, a2, an, if a1, a2, an is the family of events, then their union is also an event.
So what is the symbol of family? Like F or F1?
F is basically collection of, so here, so let me write down what does this property means first of all. So that is, I will explain that. So I will, what does this second property mean? So that means if a1, a2, an, these are the events, then their union is also event. So n running from 1 to infinity, an is also an event. So any any collection means itself a set, right? So any set consisting of subsets of omega, that we are calling the family F. So notation, you can write anything. If you want, you can write this F also. I'm just writing this F. So F represent, because it is collection of subsets. So therefore we need some different notation, right? So therefore I'm writing it F. It is not F1 actually. So actually what I'm trying to write is this F, right? So yeah. So do not confuse with F1. This is just F, because it is family. I'm using the family notation. Yeah. So this is F, not F1. So what is F? F is essentially collection of subset of omega. That means what? That means F itself is a subset of. Note that here, here F itself is a subset of power set of omega. So this is what? This is power set of omega. That is all the subsets of omega. So this is general definition of sigma field. This is general definition of sigma field, because if you remember, we have defined the probability function on the sigma field F. We have defined the probability function on the sigma field F, and that says that whenever we have a event, we define probability of event A, then we can also talk about the probability of the complement of the event, right? So unless the complement of the set itself belongs to the algebra of event, we cannot define the probability of that particular event, which is A complement, which is A complement. So similarly, we have used the property that the probability function is countably additive. So countability additivity we define for union AN, right? So A1, A2, AN are events whose probability we know, and they are disjoint events. Then we can find the probability of union of AN. So to define the probability of union of AN, we should know that union of A1, A2, AN is also an event. Then only we can find the probability. Right? So these are the technical conditions, and in this course, essentially we are not bothering about this condition, because we usually is going to take the countable sets, right? So whenever omega is countable, is finite set or a countable set, we are going to take the family F to be the power set of omega. So do not confuse with this probability, right? This is power set. This is power set. This is not the probability function. So this is just a kind of remark which you must have observed earlier also, but we need to explicitly mention that. So last lecture we discussed this random variable. So random variable is function from omega to r, and since we are going to take all the subsets of omega, this property is anyway going to satisfy. So we don't need to check this set is an event, because we are taking power set. So all the subset of omega are events. So this will be satisfied directly. So that means we are going to essentially consider this definition as a random variable. So for us, what is a random variable? Random variable is a function from sample space to R, sample space to R. But just if we want to look what is this set, then this set is essentially all the points in the domain, all the points in the domain whose value is less than equals to x. So that means it is inverse image of the set minus infinity to x. Okay, because x is a function from omega to real line. So we take all the points which are less than x and we'll find all the w such that xw is x. Xw is less than x, less than or equal to x. So this set is essentially this set. This set is essentially this set. Okay, so so using the random variable, we have seen some examples also. What are the examples? Examples we have considered are, if we are throwing two rolls of a die, then outcome is essentially 1 to up to 6, and rolling two times, that means there are two coordinates involving 1 to 6. So what is the possible way of defining such a function? So if you have domain these, and if you want to write a real value function depending on these points, then one of the easiest way is adding these numbers, right? Adding the first coordinate and second coordinate. So that is a random variable because it is a function from omega to real number. This is a real number. Same way, this is also a random variable defined on the same set, and it is taking values 0, 1, and 2. It is taking values 0, 1, and 2. So basically, how many 6's we are getting, that is this function. And the third function also is defined in this way, which is also a random variable. And the last example is we have a uncountable sample space. So we know that intervals are uncountable sets. On the intervals, we are defining this family F, that is class of events or algebra of events. So that is, if you want to define omega, x from omega to r, then we are defining the function from closed interval 0, 1 to r. So there are many ways to define this function. We will see some examples in this class also. So here it is defined in this way. So we can see that the image of this function, this is a continuous function, right? This is a continuous function. In fact, it is a linear function. So when we take multiply this interval by 3, we will get the closed interval 0, 3, and then we add 1. So it is a interval 1 to 4. So its image is uncountable. Image of this set is uncountable. So this is a random variable whose image is uncountable. The other examples has finite range, right? So these three examples, the range is a finite set. But this is an example when the range is uncountable. Range of the random variable is uncountable. So depending on what is the range of the function of the random variable, we can define, we can study its properties. But first of all, let us note down certain properties of the random variable. Properties of the random variable. So if you have a probability space, so let omega f p be a probability space and we have a random variable. So then we have the following. So we know that if you have two functions, we can add those functions. If you have two functions, we can multiply those functions. If you have two functions, we can divide those functions. So the natural property we will get here is, if you have two random variables, so if x and y are two random variables defined on omega, then so that means the following are also random variables. The first random variable is x plus y, second is x minus y, third is x into y, and the fourth is x quotient y, where y is non-zero. So how do we define x quotient y? The quotient function at w. So here the random variable is a function from omega to r. So usually the notation which we so you can see here, the notation we are using is x, w is kind of x, right? Usually we have f of x is y, right? So input x, output y. Here we are, because w is element of the sample space, we are using notation w as input, output is x. So if we apply basically the quotient function, if you have two function quotient f divided by g at x, so what is this value? So you know that it is essentially fx divided by gx, right? But we need the condition that the denominator function should be non-zero function. The same way here, when we have two functions x and y, omega from x and y from omega to r, so we define it as x omega divided by y omega, or w, whatever you call. So what are x and y? X and y are random variables. So here we are using the property that the codomain is a real number, right? Because we are dividing the elements of the image set of the range, right? So addition may not be there in the sample space, but since the codomain has are real numbers, we are defining these functions. So it is clear that if x is a function from omega to r, y is a function from omega to r, then x quotient y is also a function from omega to r. So therefore, it is also a random variable. So this is a random variable. Similarly, you can check these three are also random variables. These three are also random variables, where here we are not taking composition, it is a point-wise multiplication of two functions. So f into g at x is fx into gx. So that is multiplication of functions. So this is first remark. Second property of the random variable is, if x is a random variable, so that means it is a function from omega to r, is a random variable. And if we have a function which is a real value, so that means f is function from the domain which is subset of r to r, such that so the domain of f contains the range of x. Right, so range of x is a subset of D. If it happens, then the composition, we can compose f and x. So f composition x is also a random variable. So better way to write it like this: f composition x. So So why it is a random variable? Because it is again a function from omega to r. It is again a function from omega to r. So this is composing one variable with the real valued function. Similarly, if we have two variables, we can compose it with the multivariable functions. So if x and y are two random variables, and if the range of both of these functions, x omega and y omega, so this range is a subset of D. This range is a subset of D. So this is a two variable range which is a subset of D. Then f from, let us say, g function. So g from D, which is subset of R2 to R, gives a, then any function g gives a random variable g composition xy. So what is the domain of this? The domain of this is omega cross omega to R. Right. So this is essentially the two variable function. So that is from omega cross omega to R. So this type of functions we are going to study in the later part of this course when we will discuss multivariable stuff. Right. So the topic which we want to study in today's lecture, that is discrete random variables. That is discrete random variables. So what is discrete random variable? So this example we have discussed that some random variables has range finite, some variable range has range infinite, and some has infinite range which is uncountable. So if the range of the random variable is finite or a countable set, then we can study several properties of such random variables. For example, probability mass function we can study, right? So therefore we are going to focus on discrete random variables. So what is discrete random variable? Discrete random variable is, so let omega f and p be a probability space or probability model, right? And assume that x from omega to r be a random variable. So x is a random variable on this sample space omega, then we call x a discrete random variable if its range is countable. Its range is either a finite set or a countable set. So what is discrete random variable? That depends on what is the range of the random variable x, range of random variable x. In this example, we have seen that this first three example has the range finite set, so they are discrete random variable. But this example is not discrete random variable because image is uncountable. Also, we know that if our domain domain of a function is finite set, if finite set, then even though the function is real valued, the codomain will also be a finite set, right? Because input is finite, the output must be finite set. Output values must be finite set. So that is the first remark. So what is the first remark? Remark is that if our samples set is a finite set, if omega is a finite set, then x omega, that means image of the random variable, is also a finite set. So that means, and this is true for all random variable x. This is true for all random variable x. So therefore, what we are saying here is that all random variables defined on a finite set, finite sample space, are always discrete. So that means its range contains only finitely many elements. Its range contains all. So second is that same is true for same is true for same is true when omega is a countably infinite set. Countably infinite set. Because if we have suppose infinitely many elements in the domain, then the set xw1, xw2, xwn is also is at most countably infinite. So at most countably infinite means that is not an uncountable set. It is either finite set or infinite set. So is it possible that we have a, so do you know any function which is defined on some set, but it takes only finitely many values? So for example, R2R, what is the function which is, the domain R is uncountable, but its image is only finitely many points. So there are in the range only finitely many elements. So you know such a function, for example, the sign function, right? So either positive, negative, or zero. All the real numbers are either have positive sign, negative sign, or zero has no sign. So zero we assign the value zero. So that is an example of a random variable over a real line, for example, real line. So let us see one such other example. So can you give an example? So you have seen various examples in this course, different sample species. What is the example of a sample space which is countably infinite elements? So omega, what is the example of omega, which is not a finitely many elements, countably infinite elements? So we have seen several experiments, right? Tossing a coin throwing dice. So what is the experiment which has countably infinite outcomes? If we toss a coin, there are only two outcomes. If we throw a dice, then throw a die, then only six outcomes are there. That is the finite set. So there, the outcomes are finite. So any function we define on those sets, any random variable, they are automatically discrete random variable. So we want to see on a countable sample space. So what is the example of a countable of a sample space which is countably infinite? Countably infinite means we can form a sequence kind of thing and write down that. So if you recall, there were one experiment was discussed which has infinitely many outcomes. So that is related to tossing a coin. So what is that experiment? So let me write down the experiment. You will write down that. So our omega is essentially h, th, tth. So what is this experiment? Can you tell me? So anyone is listening or I don't know.
So tossing a coin until we get at least one
At least one,
head.
until we get the first head, right? Until we get head, right? So that is correct. So you know all these things. So uh, yeah, so this is an experiment related to tossing a coin until we get first head. We get a head. Head we write by h. Yeah. So until we get head, we are tossing the coin. So first possibility is we get directly head, or we get tail and head and all that. So this you already know. So now the question is we want to define a function on omega to r. So that is a random variable. So now you tell me how we can define a function on this set. So we need to assign which each element we need to assign a real number. So what is the obvious way to define this random variable? So you define by you tell any function which we can define on this. So what will be xh, th. So we need to just write down here what are the real numbers we want. Yeah. So what do you want? So what you can suggest?
Count of tails.
Pardon? Count of tails.
Yes.
So count of tails, if we assign, then what is the first? How many tails are there in H? 0, right? Then in TH it is 1. TTH it is 2, right? So in this way, we can assign a function. So what you said is correct, that anyway we are tossing and we are counting. So the best way to define a real valued function is counting. So either you count tail or you count tail plus 1. So if you add 1 1 1, then this will be 1, 2, 3, right? Number of tail plus 1. So depending on what function we are choosing, we can define certainly a function. So this is a clearly it is a random variable because it is defined on every element of this set, right? And we know all the values of elements of this set. So this is clearly a function. So this is a random variable. So here x is a random variable. So is it discrete random variable? So what is the range? Range is, yeah, correct. So range is the set of natural numbers union 0. So that is a countable set. That is a countable set. So this is a, so basically you can write down, so range of x, which is 0, 1, 2, is a countable set. It is a countable. Therefore it is a random variable. So essentially it is an infinite set, so countably infinite set. So it is a random variable. So this is first example. This is first example. The next example is on the same space, on the same sample space, that is T, TH. Oh, sorry, here H is there. TTH. On the same set, we can define another function. So that is a function from omega to r defined by. So you know the characteristic function, right? Indicator function. So if we select any point of this set, and we can define the indicator function. So how we define that? You define the value of any element. So for example, we choose the element h. So if we take the input h, the value of the function is 1. And if the value is not h, the input is not h, the value is 0. So y is 0 at all these elements, all these elements. Only at the edge, the value of y is 1. So clearly y is taking only two values, 0 and 1. So in the range of y. So here range of y is 0 and 1, which is a finite set. This is a finite set. Therefore, y is a random variable. The same way, we can also define a random variable which is discrete on an uncountable sample space. So for example, what I mentioned earlier, that is a sine function, that is sine function. So let omega be the uncountable set. We know that is a, let us say, -1 to 1. Any interval we can take, but since we are considering sine, so we'll take the interval involving negative points also. So if we take this uncountable set, sample space, and define the sine function. So here the sine function is defined as, so here input usually we write by w. So sine of w, that means any element of the closed interval -1 to 1 is -1 if that is a negative number. If that is 0 number, the value is 0, and if it is a positive number, the value is 1. The value is 1. So this function which we are denoting by sine because it is a sine function, from omega to r, because it is taking only three values, 1, 0 and -1, is a random variable. And it is a discrete random variable. So even on a uncountable sample space, we can define discrete variables. So this gives one remark that there are many functions which associates uncountable set to a countable set. So you know the function which is a ceiling function or a step function, or basically it is a integral integer part function of a real number. So the image is a countable set, right? Image is a countable set. It is defined on the real numbers, but it is a countable set. So we have the first remark that if x is a discrete random variable, if x is a discrete random variable, so discrete random variable means its range is finite. Its range is finite or a countable set. Finite or a countable set. And we have another function from R to R. So G is from R to R. Then what will be range of G composition X? So since X has finite or a countable set, input of G is finite or countable, therefore output of G is finite or countable. So therefore the composition has the range either finite or countable. That means the composition is a random variable which is a discrete. It is a discrete random variable. Okay, so this is first thing. Second thing is that so X is a discrete random variable. If composed with any function from R to R, then the composition is discrete random variable. But this is not true if we take the other way around. So suppose if we take a variable which is not random, and if we compose with a function from R to R. So let us take a uncountable set here. So if we consider the sample space which is uncountable, and we want to define the random variable from omega to R. So that means close interval -1, 1 to R, which is a subset of R. So if we have a subset and we want to define the map in the set, the trivial way is identity function. The trivial way is identity function. So let us define the trivial function x. So and x is defined by x omega is omega. X omega is omega for all omega in the interval. Omega in the interval. So then in this case, if we have a function from R to R, if you have a function from R to R that takes values only finitely many. So for example, we can take a function like sine function. So consider the function g from R to R defined by, so we are using the same idea of the sine function which takes only two values. So if x less than equals to 0, we can define value -1, and x greater than equals to 0, we can define the value 1. So this is very similar to the sine function. Now if we compose these two functions x and g, so therefore g composition f is a map from omega to R, this x, okay, is x. Uh, so this function takes, since the range of G is finite set, has this composition has a finite range. Has finitely elements. So basically at most 2 elements. So therefore x is not discrete, but decomposition x is discrete. Decomposition s is discrete. It is a discrete random variable. So if x is discrete, any real valued function g we take decomposition x is discrete, but same is not true if x is not discrete. X is not discrete. So that is this example. That is this example. Okay, so now we want to discuss certain properties of discrete random variable. The first property is probability mass function. So if we have a discrete random variable, we can find its probability mass function. So what is the probability mass function? Let us take one example. So we have considered one experiment earlier. That is again tossing of a coin, but here we are tossing 2 times. So consider the experiment of tossing a coin 2 times. Tossing a coin 2 times. So if we toss a coin 2 times, then what is the sample space? Sample space is basically, we know that it is either HH, HT, TH or TT, right? Because either we get head or tail. So let us make a table of these. So first is sample space. So how many possibilities? HH, HT, TH, TT. So now we want to define a random variable here. X from the set HH, HT, TH, TT to R. So again, this is the tossing of a coin, and what we can count is we can count either head or tail. So the best way to define the random variable is we can count how many heads are there or how many tails are there. So essentially both of these random variables are same. We are counting either H or T. So this defined by H of W is number of heads in W. Right. So basically how many, so each of these is W. This 4 is a W. So what is X of HH? Number of heads. So number of heads in HH, we know that there are 2 heads, and in this we have 1 head, and 0 head, right? So that means what is the range of X? Range of X is either 0, 1 or 2. 0, 1 or 2. 0, 1 or 2. So what does this means? Range is a finite set. That means it is a discrete random variable, right? So therefore x is a discrete random variable. So this much we already know now, but what we want to do is we want to define the probability mass function. We want to define the probability mass function. So how to define the probability mass function? What we will see is we will see how many elements are there in the inverse image of 0, 1 and 2. So range has only 3 elements. Range has only 3 elements. So note that. What is x inverse 0? So how many elements are there in the inverse image of 0? So there is only one element of the sample space for which x omega is 0. That is tt. Similarly, x inverse 1. So that means what are the outcomes in which there is only one head? So that they are ht and th. And the last thing is x inverse of 2, right? Because only 3 elements are there in the ring. So we are finding inverse image of all the elements, all the elements. So 2 heads are there in HH. So in this experiment, we have defined the random variable. And then we have found all the elements in the range of that random variable. And using every element of the range of the random variable, we have found the pre-image or inverse image, whatever you call, right? Inverse, yeah, pre-image you call or inverse image you call. So x may not be invertible, but x inverse 0 means all the w's are that xw is 0. xw is 0. So w are tt only. W are tt only. What this is forming, the possibility of the range, there are only 3 elements. So these 3 elements 0, 1 and 2 are essentially finding the partition of omega, partition of the sample space, because each of these sets are disjoint sets and their union is omega. Their union is the sample space. Their union is sample space. And then we know that we have a probability function on the sample space. Probability function on the sample space. So what is the probability of this? That is probability of getting tt. So tt is one outcome. There are 4 outcomes. So that means the probability is 1 divided by 4. Right? Similarly, the probability of this event is essentially 1 by 4 plus 1 by 4, that is 2 by 4, and that is nothing but half. Similarly, probability of this is half. Probability of this is half. So what is the total? I did mistake, right? This should be 1 by 4 because only one element is there. Here we have 2 elements. So what is the total? 1 by 4 plus 1 by 2 plus 1 by 4. That is 1. That is 1. So if we define this probability of this event as function of random variable at 0, function of random variable at 1, function of random variable at 2, right? So this, if we define this, so let us write down with some other color because we have not defined this. So that is essentially the probability mass function. So what is probability mass function? So this x is essentially this value. in the range. So this function is known as probability mass function. So we have not defined probability mass function. Let us define that. So definition. So if you have a random variable which has uncountably elements in the range, obviously we cannot define such a function at every point in the range because there are uncountably many elements. So therefore we are considering the discrete random variable. So it has only finite or countably elements. So therefore we can find probability of every element. All the events corresponding to each point in the range. So let us define this function. So let x be a discrete random variable defined on a probability space omega f and p. Right. So this p is basically the probability of the events. That we already know. Let x be a random variable defined on the probability space. Then the probability mass function which we briefly say PMF is defined by. So what is this function? This function gives every real value to a real value, right? Because 0, 1, 2 are real numbers. 1 by 4, 1 by 2, 1 by 4 are also real number. So briefly say probability mass function is defined by fx is a function of so probability mass function fx from R to R is defined by. So definition is this. What does this is? This says that fx evaluated at x is probability of x equals to x. What does this mean? This means this symbol px equals to x means probability of all those sample points such that x omega is x. So what is the remark? Remark is that here we found probability of the points which are in the range of x. So if we have a point which is not in the range, then what will be this set? If we take small x is not in the range of capital X, then what will be the pre-image? That will be the null set, right? Because there cannot be any point which map to that point. So therefore it is not in the range. Clearly, if x is any real number, which is not in the range of x, in the range of the random variable x. So that means there is no w such that xw is x. So therefore this set is a null set. So whenever x is not in the range, this function at that point is 0, because probability of null set is 0. Zero. Zero. So that means this function we need to find at only those points which are in range. Only those points which are in range of the random variable x. So probability mass function depends on the random variable. It depends on the random variable. So whatever random variable we take, we need to find its range. At each point of the range, we need to find the value of fx. So other points fx is 0. Other points fx is 0. So if you draw this graphically, if you draw this function graphically, it is a function from R to R. So we can draw the graph. At 0, the value is 1 by 4. At 0, the value is 1 by 4. Right? So let us use some other color. So 0, the value of the function is 1 by 4. At 1 and at 2, we need to find the function. So at 1, the fx is half. Fx is half. And again at 2, fx of 2 is 1 by 4. 1 by 4. So total is 1. And we got these frequencies essentially at these points. So this is the outcomes are only 3, 0, 1 and 2. If we have countably many outcomes, we get more vertical lines. We get more vertical lines. So this is the reason why we call it a probability mass function. So we can express it graphically and study several properties. Okay, so this is the example which we discussed in terms of head and tails. Now, this probability mass function has certain properties. So first property is that probability mass function takes values which is non-negative. Right? These all three values are non-negative. Its sum is 1. That is a total probability. Total probability is probability of the sample space, which is 1. Okay, so let us write down all these properties. So this is a proposition. So the properties are very simple to prove. Properties of probability mass function. So using the properties of P, we are going to study properties of fx. So like probability of null set is 0, we got fx of x is 0 on the range of, for the points which are not in the range. So let us start with the discrete random variable. So let x be a discrete random variable. And fx, so simply we write f, right? So if we know that which x we are discussing, then simply we write the probability function to be f. So and let f be the corresponding probability mass function. So then the following holds. Following property holds. The first property is that value of the mass function is always non-negative. for all real number. The second property is that the points in the domain such that fx is strictly greater than 0, right? Fx is strictly greater than 0 is a finite set or a countable set. Countably infinite set means essentially sequences which are one-to-one correspondence with sequences. And the third property is that the total probability is 1. So that means summation of x such that fx is 1, where summation is taken over all x in the range of x. So all summation is of all elements in the range. So proof is very simple. So first property is clear because probability is defined using the probability mass function is defined using the probability function. And probability of any event is always non-negative, right? Because fx is essentially probability of x equals to x, which is always non-negative for all x, all real number x. Second property is that we have fx greater than 0. So we have seen that fx is, if x is not in the range, then fx is 0. So that means we are considering all the points which are in the range, right? Because it is positive. So x belongs to R, fx is greater than 0 is a subset of range of the random variable. So, and x is discrete. X is discrete means this set is finite or countable. So all the subsets should also be finite or countable set. So therefore, this set is finite set or a countable set. So that is second property. This set is a finite or countable. Now the last property we need to check, that is essentially to show here that 1 by 4 plus 1 by 4 plus 1 by 2 is 1. So why this is happening? Because we have mentioned that these three sets TT, HTTH and HH, this three set which is inverse image of these three sets 0, 1 and 2 forms the partition of the sample space. And the probability function is countably additive. So that is the reason of this third remark, the third part of this proposition. Note that if x and y are any element of the range such that x is not equals to y, so if you take any two different elements in the range, then x inverse of x intersection x inverse of y is a null set. So they are disjoint sets. And if you consider all the elements of the range, that will cover all the elements of the domain. Also, omega is essentially union of all the elements in the range of the random variable of x inverse of x. So they are disjoint and their union is omega. So if you have disjoint union, if you have union of disjoint sets, then we can use the probability function is countably additive. So disjoint rule of the probability function. So that will give us summation probability of x inverse singleton x, right? And that is essentially, so what is this probability? Probability of the full sample space is 1. And here we have, what is this? In our notation, it is fx. It is fx. That is a probability mass function at a point x. Fx evaluated at a point x. So here we have defined the probability of getting the inverse image of a single set, inverse image of a single set. But we can define inverse image in general for any subset of the codomain, right? Let us see one remark, that if we have any subset of R, any subset of real line, then the probability function of x belongs to S. What is this means? So this means probability of those elements of the sample space such that xw belongs to S. So essentially this is inverse image of S under capital X, right? So what is this? So this is essentially, we need to take all the union, right? We can take the we can represent at a union over S, union over S. But S may contain the points of the range of X, and X may not contain the points of the range. If it is not in the range, the probability is 0. So therefore we need to add only those points in the set which are in the range of the random variable, and probability of those events. So this will be clear in a minute if we take any example. So let us take one example. So in the above example, of two tosses of a fair coin, So in that experiment, what is the probability of, so find probability of x belongs to S, where S is the set 1 to infinity. S is the set 1 to infinity. What we will do first, we'll first find S intersection the range of X. S intersection the range of X. Note that range of X is either 0, 1 or 2. Right, we seen earlier, it is either 0, 1 or 2. So getting number of hits. So what is S intersection Rx? So this is our interval. So all the real numbers which are greater than equals to 1. What are the real numbers which are greater than equals to 1? So that is either 1 or 2. Right? Either 1 or 2. So this is the set. So now the question is, therefore, what is probability of x belongs to S? So that is essentially summation over elements of the range which are belongs to S. So that is there, these two only. So x belongs to 1, 2, probability of x equals to x. So that is essentially probability of x is 1, plus probability of x equals to 2. So what is probability of x is getting one head? So that is half. Getting two head is 1 out of 4. Getting one head is 2 possibility, HT and TH. So now this is essentially 3 by 4. So if you take LCM, we get 3 by 4. So what does this represent? This represent either getting one head or two heads. Getting one head of or two head. So that means is the probability of getting either one head or two head. That means getting at least one head. At least one head. Probability of getting at least one head is 3 by 4 in this experiment. So this is a probability function. We have a discrete probability, discrete random variable defined on a sample space. Then we can find the corresponding probability mass function. So I am giving you an example as an exercise. So you just verify this. You will be able to verify easily. So we have a sample space. So let sample space contains 3 points. So first point is W1, W2, W3, right? We consider the family F to be power set of omega, right? So this is not a probability function. Just keep in mind that whenever we say F is P omega, that means we are considering all the subsets of omega. In fact, we don't need to write this every time. We can keep this in mind. So define P from the probability function P by we need to find probability of all these three elements. So the easiest way we can define the probability is probability of W1 is 1 by 3, probability of W2 is 1 by 3, probability of W3 is 1 by 3. So we have given the equal weights. So now define three random variables. So define x, y, and z, three random variables which are functions from omega to r by. So we need to define it on these three elements. So let us define x w1 to be 1, x w2 to be 2, x w3 to be 3. So this is first random variable. The second random variable y we are defining as x w1 is 2, y w2 is 3, and zw3 is 1, right? And the third function we are defining, that is the similar way. So these are the three random variables. So these three functions are different. Why they are different? Because at w1 the first function takes value 1, second function takes value 2 at w1, and the third function takes value 3 at the third function, z w1 is 3, but their range is same. Range of x, y, and z is 1, 2, and 3. So question is whether the probability mass function of fx f corresponding to x random variable, what is the probability mass function of f corresponding to y variable, and probability mass function f corresponding to the random variable z. So you find out this, and so we need to prove that these three functions are same, right? So just check that whether you are getting that or not. Okay, so this will be enough for